Oh, I could have watched the video from yesterday to figure out exactly where we had left off at. It just dawned on me. Okay. Last time we were finishing, not 3. We were finishing up an event or a collision that I call a 2-to-1 because we have something like this going on. And I'm going to be a little more explicit on this guy. I will make them a little bit bigger because what's the idea of what's happened with these two because of the collision? Physically speaking. Michael?
They, like the two individual objects come together as like one?
Yeah. They ended up colliding and sticking together. And so we called this one 1 and this one 2. And when we set up the math for it, it looked just like the situation when we did 2-to-2 because we had M1 V1I plus M2 V2I. Now on this side, initially, we did have somebody say, well, let's call this 3. So we could call this M3 V3F because this is after the event. Oh yeah, and I'm going to correct just so this stays kind of like I had in your picture. I had my little starburst kind of thing here because that's where the collision happens. But we pointed out if these two end up colliding and sticking together, that means this thing that we call M3 is just the sum of these two M1, the M1 and M2. So instead of calling this M3, we introduce parentheses, and we call this M1 plus M2. All right? Now, this is where it gets a little tricky, okay? And it's tricky because of the subscript. And I'm just going to go ahead and write it in a particular way. I'm just going to call it, I'll put a comma here. I try different things every year. We're going to see if this works. I'm going to call this V12F. Now the reason I call it 1-2 is to re-emphasize that our two objects that used to be separate are now stuck together. Now I'm going to try and tell you why I'm always a little nervous about doing this. Because one year, when I taught this, I used this subscript with the idea that this meant that 1 and 2 were like stuck together. Unfortunately, because I used this, what do you think people wanted to do with this number and this number? They wanted to add them and say, oh, isn't that this? No. So after that happened, and I looked at it and I'm like, okay, I could see why you could kind of mess this up. I did that. Guess what I got?
Divide.
Yeah, don't we just divide those? I'm like, no. Okay? I have tried a variety of things. None of them have perfectly worked. Sometimes I think maybe leaving this as M3V3 might work, and then off on the side we'd have like M3 equals M1 plus M2, but I don't think that looks as nice in the setup here. So remember that this V12 is simply the velocity of 1 and 2 now stuck together. Now I just had one thought. You could do this, something like that, to show that they're stuck together, because this we'd say is 1 plus 2. So I'm going to leave that up to you. Just remember that this velocity over here on the final side is a different velocity from these two over here. Okay? Now I'm going to go back and put my comma in there since I was doing that originally. Okay. What was the name for this type of interaction where you have two or more objects that when they come together and collide, they stick together? There was a word that went with it. Who has it in their notes?
Inelastic.
Inelastic. So if in a problem they say there are these multiple objects and then they say they undergo an inelastic collision and they don't tell you much more than that, that is your information that this is what's happening. Okay. So this is a second type of interaction. Now we're going to see how flexible you are. Bringing out different color. What if I said we have a 3-to-1? Can somebody tell me what to do with my picture to create the picture for a 3-to-1? Maria? Okay, we add one here. We call it 3. All right, I'm not going to bother to try and make it like even bigger, but what would I add to this here? I would add +3 because all three of them are stuck together now. What would I do here? Okay, Andreas?
Add M3 times V3I.
Perfect. And I'm not going to do it past here just because there's not room. So I'll put it here. M3 V3I because I have to accommodate the third object. And then what else would I have to do? Okay, Julian?
You would add M3 to M1 plus M2.
Right. In here, I would need to put M3 because they're all stuck together now. And then what else would I need to do just for notational purposes here?
Add a 3 after this.
I'd add a 3 after this to show that is the velocity of all three of them now stuck together. Okay? So I hope that by doing some of these problems, you get the idea that when someone says, what's the equation for the law of conservation of momentum? Is there really one set equation for the law of conservation of momentum? No. What they have to tell you is, can you describe for me the situation where particles are interacting? Then I can go ahead and create the appropriate equation based on that. Okay, so far so good? We have one more to go over, and then we can say we've covered just about all of the basic situations. So I'm going to erase this now. And here's the last one, at least to get us going. Okay, now just for fun, I'm going to throw this out there. If I yielded the pen to somebody, could you come draw me the picture for this? Okay, Michael. I'm off camera now.
The video makes it a bit awkward.
What?
The video makes it a bit awkward to go up there, so.
Explosion.
Okay. Oh, see, you're already thinking ahead too. This is good. Okay, and let's see. Go ahead and now. Yeah, leave it at that, and then I'll fill in. I was going to say fill in some stuff, but it's like, How is this in picture form compared to where we just came from?
Well, in the other one we were putting them together. This one we're taking them apart.
Right. So it's like, this is like the last one, and we just flipped everything around. So where am I going to put my 1 and 2? Like for objects.
On the right side of it.
On the right side. So now instead of having 1 and 2 over here, at least as far as separate objects go, this is where the 1 and 2 go. What goes over here then?
1 plus 2.
1 plus 2. Okay? So if I go, let's come up with the math for this. How many terms will I have on the left? How many objects do I have here on the left? One. So how many terms will I have? One. How many will I have over here? Two. How will this mathematical equation compare to the one that we just came from in our 2 to 1? Because if I say, oh, exactly the same, not necessarily. But what would we do to our equation from where we just came from to get this one? Julian? We would just flip it, so that means we would have our two MV terms, and I'm going to ask for a little more information in a moment here. And we would have our single MV term over here. And what was special about the M here? It would be the combination of both of these. So I need my parentheses here. So we called these two objects 1 and 2. So we would have 1 and 2 here. And that means this would be M1 plus M2. This is still 1 comma 2. This would still be 1, and this would be 2. What would be different about our subscripts, though, for these guys, since we have flipped sides?
Initial velocity would be on the left.
So this, where it used to be the final velocity where we came from, now it's initial. And what's over here?
Final.
And these, instead of being initial, are final. Okay? Now, can somebody think of a situation that would cover this? You kind of brought something up that I'm going to come back to in a minute, Michael. Gage?
An explosion.
Okay, that was the term. Now, if we had a real explosion, would we only get 2 things? Probably not. We would have way more pieces. But the idea is that when something explodes, you still have the same amount of mass after the explosion, but now you just have all these little smaller pieces flying off in all directions. Now, that exact situation is way more complicated because things go in all directions. When we apply our momentum stuff, we're going to live in one dimension where things go one way or the other. But I do want to bring, can somebody think of a particular explosive device that you might, because I have one that comes to mind, but I don't know if people go, oh yeah, I know what those are, and if not, then it's a worthless example. But I tend to think that most people go, yeah, I know how that thing works. Okay, Gage.
Bullet.
In what sense?
Well, there's 2 parts of it.
Okay.
Separate. They were previously one thing, but they separated.
Oh, excellent. So you're going way beyond what I was thinking. You're talking about when the bullet actually gets shot out of the gun, that the bullet has its explosive material inside, and when that gets detonated, the 2 pieces separated. So that truly would be a 1 to 2 scenario, and one of these pretty much doesn't do anything, and the other one gets shot forward. Now, in keeping with that, can any now, I'm thinking space travel here. Anybody ever?
I think I know what you're talking about. It's like when the rocket ship comes up and like the lower half jettisons and falls off.
Yeah. When you have a multi-stage rocket, the whole idea is that the lower stages, when you ask what's in there, fuel. That's pretty much it. Because they need massive amounts of fuel in order to work up to the velocity necessary to escape the planet's gravitational pull. But after they drain all that fuel, they have the mass of the empty stage left, which is a waste, so they jettison it, and they do that by having little explosive devices that will kick the used up stage backward, and then you usually have another fuel based stage that can keep going. And some rockets have multi stages, not just two. They might have three stages, so they might have that same thing happen again further down the line. Okay.
Don't they like actually land them? Like,
What?
don't they actually like now land them? Like that's what they.
Well,
do.
some right. I'm not all of them, but now because of we'll call it to be eco-friendly, we do have the design where some of these lower stages that get jettisoned, they don't just like let them fall. They bring them back to Earth, and they have like a backup fuel so that they actually can land them back and then reuse them on future missions. Maria, did you have something?
I was just thinking of fireworks.
Fireworks, okay. Mine's not fireworks, but it's based on that idea that a firework goes up, and when it detonates, little pieces go off in all directions, and you see the trails. It looks really beautiful. I get, maybe I'm more, war oriented. I think of a grenade, because if you have a grenade, when it finally detonates, it breaks apart into multiple pieces that get shot off in all directions. But the idea is that all of that momentum that you see going off in all directions, this is an interesting thing about, let's go to, fireworks is much prettier than my example, so let's go with the firework thing. When the firework gets up there, and we're going with the idea that it gets launched up, and then it slows down, and then it stops, and now it's ready to burst. How much momentum does it have when it's just sitting there?
0.
0. Then it explodes. Is there momentum as you're looking at all those things spread out? Absolutely. But how much total momentum does there have to be based on our law? How much was there before it burst? 0. So how much does there have to be after it bursts? Put it together. What? 0. But is there momentum in the little particles? Oh, this is going to be good. We get the canister, it gets up, nothing's going on. Then, I got to do this in color because it would be in color. We'll say it's red. We got little particles. We got little particles going off in all directions. If I looked at just one little particle and it's moving off in its direction, is there momentum there? Is there a mass? Is there a velocity? Yes. So if I just looked at that little guy and said, there's momentum there. There's momentum here. There's momentum here. There's momentum in all of these individual pieces. How much momentum is here, though? How much was here?
0.
So how much has to be here? 0. How is it that I could say, well, that guy has momentum, that guy has momentum, that guy has momentum. All these little pieces have momentum, but overall, I got 0. Can someone figure out a way to explain that?
Because they all pushed at the exact equal back. So it's kind of like you showed us when you had one break, and then it transferred it there, and then it hit, and then the one in the middle stays the same because
you're
they're
close.
going off.
When you talked about them going off, that's kind of the key thing. Let me ask you this math question. How could I have two actual numbers but actually have a sum of 0?
Negative.
Be more specific. Give me an example.
Like
Well, yeah, if you did, like, maybe one's positive, one's negative, and they cancel each other out.
Okay, so give me a specific example then.
2 minus 2 is
So,
0.
and the idea is not so much 2 minus 2, but it is 2 plus what?
Negative 2.
-2. Is that helping you at all here? Why is it that we could still say, damn, I got all that mass moving all over the place. How can you tell me there's 0 total momentum there?
Because maybe something's being taken away.
Michael?
Because all the different particles are blasting off in different directions, so they cancel each other out.
It's the direction thing. So your concept of a 2 plus a -2 equals a 0. Well, that means there's 2 actual values, but they add up to 0 because they're opposite each other. When it comes to momentum, because momentum is a vector, it involves direction. So if you have particles that are headed off in this direction here, there is momentum right there that you could talk of, but somewhere over here, you will have an equal amount of momentum that is headed in the opposite direction. And because the idea here is that we're always adding all of the individual pieces of momentum together, it's kind of like this momentum going in one direction is balanced or canceled by an equal amount of momentum that's going in the opposite direction. Now, in the case of a fireworks, this is a pretty complicated example because it's like a 3-dimensional example of that because the thing bursts out in all directions. But that's the idea that you want to remember about this idea of an explosion, because most of the time when you think of an explosion, people think of this part of the explosion. They're like, oh, everything gets shot outward. But if the thing that was exploding was just sitting there before the actual explosion happened, it actually has no momentum whatsoever. So when it explodes, there is still a total of no momentum, but it's because the explosion causes momentum to be generated, but it generates, in a sense, equally in all directions. So overall, all that momentum still adds back to 0. Okay? Wow, that's a good example. Okay, so you guys have 3 equations now involving the law of conservation of momentum. I'm just going to throw this out at you. Oh, I did orange last time. I'm going to have somebody take us through this. Can you adjust this for me? Okay, Stella?
Add a third circle to the right side
Okay, so over here, we got 3 particles now.
and plus 3 in the bigger one.
We got to add all of them together here. And then how do we adjust down here in the math?
Plus M3
We add an M3 term here.
and then add comma 3.
We could add that, just so remember they all start together.
Yeah. And then on the other side, plus M3 B3M.
Bingo. Okay? You get this a little bit? Okay. I was going to dump problems on you. We'll wait till Monday. So on Monday, we are going to take a look at the worksheet because the second and, well, the second page, which has a total of 1, 2, 3, 4, 5, 6, 7 problems, these are all conservation of momentum problems. So you'll be using some version of the equations that we've played with over the last 2 days. And then the last page, which has 1, 2, 3, 4, 5, 6, that one kind of has a combination of different styles of problem. So I am thinking that we'll definitely do one more homework problem turn-in from this second page, where it's conservation of momentum oriented. Then we'll see about that last page. Okay?
What is the last page?
The last page has a mix of problems, so they're not all the same thing. Okay, so we're done.